We're going to work through an exercise in MATLAB and Simulink on how to control a distillation column. So the thing that we're going to be able to manipulate is the reflux ratio. We can have that go up or down, and then we're going to try to control the distillate composition. Okay, in this model we have 30 trays in this column, and we have things that we can adjust like the reflux ratio, and we also have disturbances. The feed composition and the feed flow rate are disturbances, and even given those disturbances we're going to try to maintain at a certain set point. We also might want to change the set point. Here's the full problem statement. We're going to maintain an overhead mole fraction for the light component in a binary distillation column that separates cyclohexane and N-heptane. So the nominal steady state for the column is a reflux ratio of 3 with an allowable range between 1 and 10. The reflux ratio produces a cyclohexane product with a purity of 0.935, but the target composition is a little bit higher, 0.97, with an allowable range. Okay, we can be within the range of 0.96 to 0.98, and the objective is to design a PID controller to try to stay within this product specification range. So here's our manipulated variable, the reflux ratio. We have our controlled variable, the thing that we're trying to design to maintain a set point at, which is the distillate composition, and then we have some of these measured disturbances that are coming into our model as well. So the very first thing that we want to do is determine steady state conditions, and in particular we want to come up with our U bias value. So that came from the problem statement. Our U bias in the PID controller is just going to be a value of 3 for the reflux ratio. It's whatever it is when you turn on the controller. Then we want to estimate a model from this. This is going to be a doublet test that we're going to use to generate a dynamic response and fit a first order plus dead time model. Okay, let's go and grab the source files for this. If you'd like to follow along, you can. And then we'll add a PID controller in just a little bit. Okay, we'll go to the CHE 436 website, and this is going to be placed under the homework. This is a special problem number 10. You can see the link to the problem right here. If I go back and download the Simulink files, then I'll have those on my desktop. Okay, so the very first thing that we want to do is download that, and I'll go ahead and minimize this and then extract these files. So if you got to remember to extract those first of all. These are going to be the Simulink files, and I'll go ahead and open up distillation.slx. That's going to be the distillation source file for the Simulink model file. You can delete the zip folder if you'd like. The very first thing that we need to do is generate a doublet test, and so I'm going to do a up and down and then back to the nominal value for the reflux ratio. We'll start at a value of 3 and then go up and back down again. Okay, and then the other thing that we'll need as we generate this, we'll also need some, let's go and get some Excel files to help us with our first order plus dead time fit. And I'll just grab this one right here. Okay, it looks like it just opened up Simulink, so it's getting in my way there. Okay, I want to save this as, and I'll go ahead and save the special problem 3 files. I think that one has the Excel template in here. Okay, let's go ahead and open that up. Okay, here's a fit FO. This is a first order plus dead time fitting tool that we have in Excel. So I'll just put that on my desktop and delete the rest of these special problem 3 files. And okay, so we'll have that one available to us to help us fit the FOPDT model. Okay, let's see if this thing is loaded up now. Here is our here is our model for the distillation column, and we have the ability to control the reflux ratio in this. So here's the view distillate plot right here. I guess I don't want to maximize that. I'll just leave that over to the side, and you can see the reflux ratio as well. We'll have a real-time pacer here. If you'd like to speed up or slow down the simulation time. You can do that with this. I'll leave it at 3 for now, and then you can see the reflex ratio, high and low limit, and the reflex ratio there. So I'll go ahead and run this for a time limit of 100, and this is going to start calculating, and then you'll see the distillate plot there. Okay, to change the reflex ratio, I'll go ahead and just go here and change it to 4. Okay, and you're going to see the distillate composition go up. It's going to become more pure. I'll change it back down to 2. Okay, it's going to go back down again. Gets less pure. Okay, if you need to resize this, you can. And then I'll go back to a value of 3. Okay, so this is our doublet test. And it's going to finish up here at 100. Okay, and it should have produced a file for me. After this is done, there's the doublet test right there. You can see with the reflex ratio I went up and then down and then back to the nominal value. And let me go ahead and just minimize those. Let's see if it produced this. Okay, there's the data file right there, the reflex ratio. And we have the, a couple other columns here. We'll just pick out the ones that we need. You can see the 4th column is going to be, that one is going to be the reflex ratio. And the 3rd column, that is the, I believe that's the distillate composition. Okay, so let's go ahead and just use those for our, I'm going to copy this data file. And then let's go back to our FOPDT Excel spreadsheet. So this one helps us estimate an FOPDT model. The ones, columns D through F, are the ones that we're going to input. I'm going to just make a new sheet here and paste these in, and then just do data, and then I'll do text columns. And this is going to be delimited by a space, or you can do fixed width as well. Okay, and if I just select space, then I'll put those into columns. Okay, here are the times right here, and then this is the distillate composition, and that is the this one is the reflex ratio. So let's go ahead and just copy some of these in. Okay, I'll copy these into the data file. Okay, there's the time, and I can double click that to just make all those numbers show up. And then let's get our reflex ratio. This is going to be our input. Okay, come back to the data. Okay, I input those, and then let's get our final measured values. Okay, and that's going to be here the distillate composition. Let's copy that one out. Okay, so we have our model right now. We can adjust this a little bit if we want to. So for example, if I didn't think the gain is as high as it, so I can reduce it down a little bit. And let's go ahead and we have measured and model. We might need to fill down a little bit. It might not be far enough on this. It looks like the plot. Let's just go ahead and do control down. Okay, so you can see that some of these need to be copied down. I'm just going to come over here to the little box and double click, and I'll copy down those formula. Okay, so I have the prediction for the model values over this whole range, and I might need to increase the time constant as well. So let me increase that to about 100 or maybe 50, and then maybe increase this to about 0.2. Okay, so I'm getting a little bit closer. Okay, what I'm going to do now is just go ahead and try to optimize these. I'm going to use Solver to do it. I have a sum of squared errors there and a sum of absolute errors. So I'm going to come over to Solver. If you don't have Solver, just come to File, and this is going to be under Options, and then go to Add-ins, and then run Excel add-ins and make sure Solver add-in is selected, and then click OK. Okay, so then once you have Solver, you can come back here to Data, and you'll see a little Solver tab. and I'm going to set the objective equal to B11, the sum of squared errors, and I'm going to change these three values right here. I'm going to let it change the theta, this is a time delay, a tau, and the gain. And then I'm also going to add some additional constraints there. You can select add and add additional constraints if you'd like. Okay, you also have this make unconstrained variables non-negative. We want to unselect that because if the gain needs to go negative, it can. And then click solve. Okay, and we're going to watch this try to fit it. Okay, so it looks like time delay was about 3. Our time constant was about 14, and then our gain is about 0.05 or about 0.06. Okay, so let's just go ahead and take a screenshot of those. We're going to need these for the next part here. Okay, go ahead and just take that screenshot just so we can copy those in. Okay, so we performed our doublet test and we got some FOPDT, first order plus dead time parameters. And now what we want to do is obtain some PID tuning parameters. And it looks like the delay here is fairly small. If you want to use some PID tuning parameters, you can come to, I'm going to show you some simple ones that are easy to remember. We'll just come to the controller design. And we have PID tuning parameters right here, some rules for IMC tuning. Okay, let's just go ahead and use those. I'll start with a PI controller only, and we can add some derivative action if we want to. And there's some information on derivative filters. Okay, the simple ways to remember these are you just start with Kc equals to about 1 over Kp. And this is going to be for IMC moderate tuning. And then tau I equals tau P. And then we'll start with tau D equals 0. And maybe add that back in later and see how we do. Okay, so 1 over Kp is going to be about, let's see, is that 1, I think that's about 20. Okay, and then tau I, we'll say that's about 14. And so then if we put this in terms of we can put this in terms of P, I, and D parameters. P is going to be equal to Kc, I is going to be Kc divided by tau I, and tau D is Kc divided by tau D. Okay, so let's go ahead and put these into our Simulink model and see if we can have a controller now. Okay, so I'm going to come back into my distillation. Now instead of the me selecting the reflex ratio, I'm going to have a PID controller select the reflex ratio. So let's go ahead and add that in. I'm just going to come to the library, this little button right here, which is the library of different, library browser of different submodels that I can put into my model. And this one I'm going to have a PID controller. So it's going to search for PID. And I'll just drop that in, drag it, and drop it in there. Okay, so here is a PID controller. I'll go ahead and put that into my model. And that is the output of that is going to be my new reflex ratio. Okay, and then I need to have a measurement that comes back, and the measurement is going to be my distillate. Okay, it's going to be my and so that's going to be coming right from here. Okay, but I need to have a couple other things in here. I need to have a summation because I need to compare it to a set point. So let me have a constant here, and this will be my set point. I'll just go and drag this in. Okay, and my set point 0.935. I'll just do that to start with, and then we can change the set point as we go. And I'll just label that set point. Okay, and then let's have a summation in there as well. So we can drag this in. And then I'm going to change the signs on this. If you double click it, I'm going to just add a minus sign and then instead of a plus, just so it turns it to a plus minus there. Okay, there's our, oh, I did it to the wrong port. There's my set point. And let me try that again. Okay, and then I want to take off the distillate composition. Okay, and so what I need to do is somewhere in this line right here, just right click and bring that off, and that will feed in here. And then the difference of those two is going to feed into my PID controller. So let's go ahead and just come in here. Here's my proportional, the P term, which is going to be about 20. The next one is going to be equal to 20 divided by 14. So there's just some default ones. Then we go to PID Advanced. We're going to limit the output. The upper limit for the reflux ratio is 10, and the lower limit is 1. And in the anti-windup method, I'm going to choose clamping for that. Okay, and I think we're about ready to go. So let's go ahead and click OK. And you know, I think the desired, let's just go ahead and start with the desired set point, 0.97. And I'll go back to the problem statement just to check that. Okay, yeah, so the target composition is 0.97 with a range of 0.96 to 0.98. Okay, let's go ahead and have this one. All right, and let's see how well it's going to simulate. And I'll double click over here on the view distillate plot. Okay, I forgot one thing here. You see how I had a big disturbance right at the beginning? It went down and then it's going to come back up eventually, but that's undesirable. That's like when it first turned on the controller, I didn't put in my U bias value. Okay, so what I need to do is stop this. Let me go ahead and stop this one. And it's going to bring up a plot. Okay, so in my PID controller, I need to do one other thing here, which is the initial conditions. This is my initial reflux. Okay, so I have, you know, this integrator here, the initial conditions. Okay, and I have an internal integrator. I'll just put that at 3. Okay, and let's try this again. Okay, so you see it go up now directly versus kind of going down and then back up. That's because the integral term needed to initially be set to 3. So, okay, and then I can change the set point if I want to 0.96, for example, and then it's going to come down to 0.96. Okay, now I can put in disturbances. So for example, the feed rate, I can change that, and we'll see how this responds. Let's go look at our disturbances, because we need to simulate some disturbances for our problem as well. Okay, so we obtained PID parameters. We're done with that, and we implemented the PID controller, and we're done with that one. Now we did the set point from 0.935 to 0.97. We've done that one, looked good. And we might need to tune it a little bit more, make it a little bit more aggressive. And then we want to do some disturbance rejection. So this is change the mole fraction from 0.5 to 0.42. So we want to try to maintain within that target product range, even when the mole fraction of the feed changes about halfway through to 0.42. So let's go and tune this just a little bit better, a little bit more aggressively. Looks like we can go a little higher on the gain. So let me go up to 40. I'll go ahead and just double it. Double the KC values. And let's try this again. We'll just go ahead and simulate it one more time. Okay, so we can see it coming up. Oh, I have it at 0.96. Let me do it at 0.97. Okay, and this is just a little bit more aggressive. We have, you know, this, okay, you can view the reflux ratio. It's still at 10, and then it should drop off a little bit here after it reaches that value. It looks like it just reached that barely. Okay, so it stayed at 10. Okay, and actually that is the that was the upper limit. Okay, there's the reflux ratio right there. The PID controller, you can see in the black line. Just the red was the upper limit. Okay, so let's just go ahead and try be a little bit more aggressive, even beyond that. And I'm going to double it one more time. Put it to 80. Okay, and let's run it again. Okay, you can change the speed up there. Okay, looks like we're doing pretty good with that. Let's see the reflux ratio, and not bad. Okay, so it's continuing to go down. It'll reduce any kind of offset there. Okay, so I had a little bit of overshoot, not bad, and fairly smooth action with the controller. Now the next part is going to be to change the feed composition. And let's see what the controller is going to do as this feed composition changes. I'll go ahead and change it after it reaches the set point. Okay, let's go ahead and just close these out. And we will, actually I do need the distillate plot up. And I'll also bring up the reflux. Yeah, I'll bring those back up just so we can watch it. Okay, let's go ahead and start it. Okay, same as before, but now this is 0.42. And let's see what this does. So the feed composition starts dropping. The reflux ratio is increasing, and it's still within that limit. But you'll see after a certain point, the controller, even when it goes to an upper limit here, it's not going to be able to maintain that feed composition. Okay, so this is an example of a controller that did its best, but it had to saturate. It went up to an upper reflux ratio of 10, but still couldn't control the composition. So the answer to this actually is a little bit tricky. It's that it's really not possible to control it within that range, given that input feed composition. Okay, so this is an example with Simulink, and the source code is available if you'd like to download this and try it out yourself for the distillation control.